Welcome to EDU World Space.
To answer this question, so let rho equal the uniform volume charge density of the sphere, and r the carrying charge, and q and the radius. Let's let the radius equal r and the carrying charge equal q. So now that we've defined our variables, we can go ahead and write an expression to combine them together. So the rho is equal to the carrying charge over the density of a sphere, which is 4 over 3 pi, and the radius, as we said, it will be represented by a capital R, and this is cubed. So now, if you consider a shell of thickness dr and a radius of r from the center of the sphere, then its charge dq will equal this. So it's equal to, let me write that a little bit better. Oh, sorry, I erased the cubes here. So dq is equal to rho 4 pi r cubed r squared dr. So we're differentiating with respect to dr. So now if you simplify this, you're going to get that. Or if you replace rho with this following equation above, you're going to get that it's equal to 4 radius cubed, and this is on the top. So if you further simplify this, you're going to get that it's equal to 3q over r cubed, and the radius, the distance, differentiated to respect to r. So now the energy required to bring dq to the surface is b dq. So the potential on the surface of the shell can be represented by this. So the potential on the surface is represented by q over 4 pi permittivity of free space times the radius. So the total energy required for all these shells to assemble to form a sphere of radius r can be represented by the following potential. So the potential is equal to the integral from 0 to the radius and v dq. So if we replace v by the above equation, so it's equal to 0 r. Let me bring that down. And now we're integrating it with respect to dq. So if we do that, then the final answer, since we can move most of this outside, we can move the constants outside the integral, then we can simplify it into this following integral. So if we expand this integral, we're going to get pi over 3 times 1 over 4. So these are just the constants. Sorry, I'm missing a step here. So let's go back here. So now we can actually replace dq with the following, since we actually calculated that here, dr. So we can actually replace it. That's what we're going to do. So we need to replace this. So the integral, let's write it on a different line. So the integral from 0 to r is q 4 pi times the permittivity times the radius. And now you can just bring this whole thing down. So let me get this. And this whole thing is getting multiplied and replacing the dq here. So now we're substituting and we're replacing the integral, and we're integrating with respect to radius now. So now if we complete this integration, we're going to get that it's equal to 3 over 5 1 over 4 pi times the permittivity, and this is also multiplied by q squared over the radius. So for a point charge, if the radius goes to zero, then the potential goes to infinity because that's the greatest. That means that the potential is the greatest when the radius is at the center of the sphere. So this means that the point charge should have infinite self energy. And that's it for this question.